we don't have Mark Siggers as announced, but Sangi will talk about obstructions for matroids of half width at most k and graphs of linear rank width at most k.
All right. Yeah. Thanks for coming. Thanks for inviting me. It's my pleasure to talk about this work with Mamadou Kante, Eunjung Kim, and Oh Kwon. This is about the obstructions of matroids of path width at most k, and also for graphs of linear rank width at most k. Oh, we missed Linda, but anyway, yes, I will go slowly, and if you have any questions during the talk, please feel free to interrupt me. I will be happy to answer any questions. So some of you may have seen some part of the talk already. So here are the main statements of the theorem. So we proved that every pivot minor obstructions for graphs of linear rank width at most k has at most that many vertices. So that's the first consequence, 2 to the k squared. And in the same paper, we also proved that for any finite field f, the f representable minor obstructions for matroid of path width at most k has at most 2 to the size of f to the k squared many elements. So in both cases, we have a explicit bound on the size of obstructions. So these are the main theorem, and they have the same method. All right, so I'm going to go with motivations, and you have several keywords that you don't probably, I mean, you may know already because of the previous talk, but I will go through the definitions. So why do we care about obstructions? So let me begin with the minor obstructions. So Robertson and Seymour proved in their celebrated theorem that for any minor closed class of graphs, there are only finitely many graphs that characterize that class of graphs in terms of forbidden minor. What I mean is that you have a finite set such that any graph H belongs to that class if and only if it has no minor in this finite set. So this is the equivalent statement of well-quasi-ordering. And the proof is non-constructive. So this proof doesn't give you any explicit list or any method of constructing the list. And there are well-known graph width parameters like path width, tree width, and branch width. All of them have the property that when you take a contractions or deletions, then these numbers decreases. So the set of graphs having path width at most k is closed under taking minors, which means that by the corollary of this theorem, each of these sets have only finitely many obstructions. But this well-quasi-ordering theorem doesn't give you the method of constructing such an obstructions. And in 1998, Lagergren proved that there is an explicit upper bound. So for path width at most k, the upper bound is 2 to the k to the 4. So you don't have more than that many edges. And for tree width k, the minor obstructions have at most 2 to the k to the 5 edges. Okay, so because of that, we can say something, right? And also for branch width, as a corollary of more general result on matroid, we can say that minor obstructions for graphs of branch width at most k has at most 6 to the k edges. So their theorem is actually for branch width of matroid, but as a corollary, you can deduce that. So for path width of graphs, tree width of graphs, and branch width of graphs, we all now have explicit bound on the number of edges. So what we have is an analog of that to the linear rank width of graphs and pivot minors of graphs, and also for matroid. But I will talk about matroid later, because once you see the proof sketch, then it should be clear how you solve how you modify the proof for matroid. So let me try to motivate the connectivity function arising from linear rank list. I mean, for linear rank list. So given a partition of edges, usually the connectivity function is the number of vertices incident with the both x and the complement. That's a usual connectivity function in the graph. And for matroid, the usual standard connectivity function is the sum of the rank and its complement minus rank of everything. So for those who know matroid, this is the standard thing. And all these functions satisfy some common features. So we say the function is a connectivity function if it satisfies three axioms. So the first one is submodularity. So f of x plus f of y is at least f of their intersection and f of their union. This inequality is called the submodular inequality, and we have symmetric. So when you take a complement, then it shouldn't change the value. And then empty set gives 0. I mean, this is just normalizing. If you have a function satisfying 1 and 2, then you simply subtract f of empty, then it satisfies the third axiom. So that's what's called the connectivity function of a finite set. And these two functions, v of x and lambda of x, they all satisfy these three axioms. And here we have another connectivity function arising from graphs, which is useful for the study of dense graphs. So when you have a partition of the vertex set, what we define is the we look at the rank of a 0, 1 matrix whose rows are from x and columns are from y, and we put 1 if corresponding rows and columns are adjacent and put 0 otherwise. And then we compute the rank of that matrix. So this rank is called the cut rank of this cut x. And when we do that, we will assume that this matrix is over finitely filled. So that 1 plus 1 is 0. So this changes rank a little bit, right? And that will be useful later. So for instance, in this graph, when you take a partition of the vertex in 2, red versus black, then the cut rank of red vertices is simply the rank of this matrix. And if you look at this matrix, the sum of the second row and third row is fourth row, so the rank is 2. So the cut rank of this red vertex set is 2. Okay, so that's how we measure connectivity function, cut rank function. And whenever we have a connectivity function on some finite set, we can define branch decomposition as follows. So we have a pair of subcubic tree T. So this is a subcubic, which means every internal node has degree exactly 3 and all the leaf. Yeah. And also we have a bijection from the finite set V to the leaves of T. So here we have numbers from 1 up to 8 that represent the elements of V. So that's a branch decompositions. And for any edge of the branch decompositions, we have the canonical partition of the ground set. So when you delete this edge, then you have one side you have 1, 2, 3, 4. The other side you have 5, 6, 7, 8. So I compute this function f of 1, 2, 3, 4. It doesn't matter which side you choose because it's symmetric. And that gives you numbers for every edge. And then the width of this branch decomposition is the maximum number obtained by these things. So for every edge we have one number, and then I take a maximum of that. That's the width of particular branch decomposition. And then branch width is the minimum possible width over all possible branch decomposition. So you want to minimize the number, right? So if we just implement this thing by the definition, there are lots of things to consider, right? So you have many subcubic trees to consider, many bijections to consider. So there are too many things to look at. But we do have an efficient algorithm for each k, we do have polynomial time algorithm to decide whether or not there exists branch decomposition of width and most k. This is true for any connectivity function. So it's a lot more efficient than you think. All right. So if we plug in the standard connectivity function for graphs, like counting vertices meeting both sides, then you get the definition of branch width introduced by Robertson and Seymour. And if you use the matroid connectivity function, then you get the definition of branch width of a matroid. And if you use the cut rank function, then this is the definition of the rank width of graph. All right. And this talk is not about rank width, it's about linear rank width. How do we get it? And now we define path width of connected function. So we're gonna restrict the branch decomposition to something like this kind of tree. So this is called the caterpillar. So you have one spine and all the leaves are adjacent to that particular path. So if this is your branch decomposition, how are you going to measure the connected the width? Well, the edges instant with the leaf will always have a value, a very small value. So when you care is actually, when you care is the width value of these edges on this path. So alternative definition, this in the box you have this alternative definition, which is almost equivalent. What I mean is, as long as width is and these two, this will be same. If you are talking about width 0, width 1, then it could be different because of the edges instant with the leaf, but most of the time it's the same. So instead of defining in terms of caterpillars, I'm gonna define it as a linear layout. So this is nothing but a linear ordering of the elements of the graph set. So E1 up to En. And then width of the linear layout is nothing but the maximum value of the connected function value arising from the cut. So you have a ordering E1, E2, En. Then I look at these kind of cuts and then compute the connected function of E1 and connected function value of E1, E2, E1, E2, E3, etc. And take the maximum of that. That's going to be the width of particular linear layout. And then path width is the minimum width of all possible linear layouts. So that's the definition of path width of connectivity function. And then, since this is just instance of branch decomposition, so we naturally get this definition that branch width is less than or equal to path width. Now, when you plug in all the standard connectivity functions like number of vertices meeting both sides, we get the definition of linear width. There are small number of papers dealing with the linear width. And if you use standard connected function for matroid, then you get a definition of path width. And if you use the cut rank function, then you get a definition of linear rank width. So these are like smaller instances. Okay, and so why do we care about vertex minors? Because when you have the cut rank function, so if you use cut rank function, one nice property is that when you apply local complementation, then this function doesn't change. So the function value is invariant. So local complementation is nothing but an operation to replace this neighborhood by its complement graph. So if two vertices are adjacent, then you delete that edge. Otherwise, you add an edge. And the nice thing is that when you have any cut, then you look at the matrix arising from this cut. Then you have neighbors here, neighbors there of this particular vertex. Then local complementation just correspond to an operation to what? So edges between this cut is flipped. So those are here. That area, if there was 1, then it becomes 0. If there was 0, then it becomes 1. And you can just simulate it by adding this row over here. And since the field is binary, so 1 plus 1 becomes 0, so the rank doesn't change. So that's why it's nice to work with the local complementations when we work on cut rank functions. And pivoting is another operation which can be defined by a sequence of 3 local complementations. So here you have for any edge UV, the pivoting UV is nothing but 3 local computation. And here's a description how you can describe pure combinatorially. Anyway, so this is the key fact. When you apply these operations, the cut rank function doesn't change. So that's why we can talk about vertex minors and pivot minors when you study rank width and linear rank width. And so we say that small graph H is a pivot minor of big graph G if H is obtained from G by a sequence of vertex deletions and pivoting. And these 2 operations never increases the cut rank function value. Like in a matrix, you can delete row or column and rank doesn't increase. And same for vertex minor as well. So for vertex minor, we define by a sequence of vertex deletions and local complementations. Right? So, because, yeah, okay. Now, let me talk about pure minor obstructions and vertex minor obstructions. So circle graphs are the key examples for vertex minors. So circle graphs are intersection graphs of chords in a circle. So you have a circle and you draw several chords, right? And then so if this is chord 1, 2, 3, 4, 5, then when you get is when you draw is 2 vertices are adjacent if they intersect. Maybe this example was too simple, but anyway, that's the circle graph. And Boucher proved that graph is circle graph if and only if it has no vertex minor in these 3 graphs. So these are not circle graph, and those are vertex minor obstructions for being a circle graph. And Jim Geelen and I had a theorem in 2009 characterizing circle graphs in terms of pivot minors, and there we have 15 obstructions. And actually, this theorem implies the Grotowski-Wagner's theorem on planar graphs. So graph is planar if and only if it has no K5 and K33 minor. We could deduce that. Anyway, so talk more about the conjecture. So Robertson-Seymour's theorem says that every minor closed class of graphs have finitely many minor obstructions. So we conjecture that same is true for pivot minors and vertex minors. And obviously 1 implies 2, but furthermore, it's actually, it may be strange, but 1 actually implies the Robertson-Seymour's graph minor theorem. So 1 is a lot stronger than, so this 1 contains all the, many of the known theorem on well-quasi-ordering. And we have a special case. So if pivot minor closed class has bound, so for any pivot minor closed class, there are finitely many pivot minor obstructions of bounded rank width. So you might have infinitely many obstructions, but if you cut for any fixed constant k, then up to that rank width k, you have only finitely many obstructions. So as a corollary of this, you can deduce that for linear rank width and for rank width, the list of obstruction is finite. So for each k, class of graphs of linear rank with at most k has finitely many pivot minor obstructions because all the obstructions will have a linear rank with at most k plus 1. So deleting a vertex can decrease the linear rank with only by at most 1 because you delete one row or one column. That's it. The rank can only drop by 1. So obstructions will have linear rank with at most k plus 1, and when we combine with this theorem, then we already know that there are only finitely many. Same is true for rank width. Right? These obstructions have rank width exactly k plus 1. So therefore, because of this theorem, there are only finitely many obstructions, pivot minor obstructions. Bounded rank width doesn't imply bounded linear rank width. Oh, but bounded linear rank width implies bounded rank width. Yeah, so here you have, so for the first case, each obstruction has linear rank width exactly k plus 1. So therefore, rank width is at most k plus 1. So that's why we can apply this. All right? Yeah.
Is it easy to see that one implies the theorem on the left side? If I understood the definitions correctly, one implies 2 is...
One implies 2 is obvious, right? So one implies the Robertson-Simmer minor theorem is relatively easy. So basically, you have to go through the binary matroid. So this theorem, bipartite graphs. So if you prove 1 for bipartite graphs, then that implies Robertson-Simmer's graph minor theorem. But this is true. So when you restrict this to bipartite graphs, then what you get is actually a well-quasi-ordering of binary matroid in terms of minor operations. So pivot minor correspond to the matroid minor when you restrict to bipartite graphs. So pivoting operate. So what you do is when you have a binary matroid, you pick a base and then take a fundamental graph, which is a bipartite. Now, the pivoting operation corresponds to an operation of choosing a different base. So when you have a binary matroid, you pick a base, then you draw fundamental graph based on the fundamental circuits. But if you choose different base, then you have a different graph, and these two graphs are related by pivot operations. And the matroid contraction deletion correspond to like pivot and delete. So depending on that. So, and we have this written down in my paper. So indeed, yeah, so this is actually, so for bipartite case, this is a theorem, right? If Jim Geelen and Gerards and Jeff Whittle write down all the paper, then it's a theorem. Yeah. All right. What do we know about rank width? So for rank width at most 1, the obstruction is precisely known. It's exactly 2 graphs. So graph has rank width at most 1 if and only if it has no pivot minor isomorphic to C5 or C6. And Boucher never mentioned this, but his theorem immediately implies that this is the case. And I had a paper back in 2005 saying that pivot minor obstructions for graphs of rank width at most k as at most 6 to the k plus 1 vertices. So it's a single exponential function. And last year, no, not last year, 2 years ago, I uploaded some paper on arXiv improving this bound for the case when k is 2. So if you plug in this number, then you get something like 40 something. But I was able to reduce it to 16. And I used to have a computer code to search all of them, but it never ends. And why do we want to have explicit bound? Once we have explicit bound then you can say something. So the interesting fact is that there is some logic formula to describe vertex minus and pivot minus. So with Bruno Crucel, we were able to show that one can express in terms of modulo 2 counting monadic second order logic formula that a graph contains fixed graph H as a pivot minor. And that means, Krusell-Markowski-Rotix has a theorem that if you have graphs of bounded ranks, you can decide whether or not fixed logic formula is true in polynomial time, in a cubic time. So when you combine these things, you can decide in cubic time whether or not given graph has rank width at most k, or fixed k. Yep. Oh, you mean the constant hidden in big O? All right, so it depends on like alternation depths, right? So how many quantifier you use, right, in the logic formula, and then also number of equivalence classes of logic formulas up to that quantifier depth. And I think my logic formula has like exists some set, exists some set, exists some set, and for all something. So probably quantifier depth is like 4 or 5 or something like that. And then now we have to count number of formulas up to equivalence. Yeah. Anyway, it's huge. It's huge. I don't want to compute. Yeah, I mean it's more like a black box to me. Anyway, once you combine this, then we can now say that we have a cubic time algorithm to decide rank width at most k, instead of saying there exists a cubic time algorithm. So, right, if we didn't have explicit bound, then, well, by this theorem, I know that there exists some obstructions. So once we have obstructions, no, we don't have obstruction, but we know there exists obstruction. So there's a difference, right? So, which means that we knew that there exists a polynomial time algorithm to decide whether or not rank width is at most k. But without using this explicit obstruction, this theorem doesn't tell you what algorithm it is, right? Because we have no idea how to find the obstruction. But now we do have an algorithm to generate the obstruction. Simply spend constant time to enumerate all graphs up to that many vertices. It's a constant time algorithm, independent of the size of the input. So yeah, so you can just enumerate all graphs up to 6 to the k. Okay, now you have a complete list of forbidden pivot minors. Okay, then now you're ready to run this algorithm. All right, so that's why we have it. But actually, we have a better algorithm, but I will tell you later. How about the linear rank width? So for linear rank width 1, we already have an explicit list of obstructions. There are precisely 8 graphs for linear rank width 1. So this was due to Adler, Farley, and Proskorowski. And they proved that graph has a linear rank width at most 1 if and only if it doesn't contain any of those 8 graphs as a pivot minor. They also have a forbidden vertex minor as well, but I only showed you pivot minors. And Mamadou Kante and Oh Jung-kwon tried to extend this for a higher value for linear rank width. And what they managed to do it was that for any k, the obstructions for pivot minor obstructions for graphs of linear rank width at most k, well, they don't know how many are there, but among them, if you look at the rank width 1 case, then you don't have many vertices. So the rank width 1 pivot minor obstructions have at most this many vertices. Right. But there could be more rank width 2, 3, 4, etc. So here's our theorem, right? So we have 2 to the 2 to the k squared for the pivot minor obstructions. And because of that, we can construct the logic formula to decide the linear rank with the most k. And this was open, so we didn't know how to construct such a logic formula. And also, as a corollary, we have a cubic time algorithm because of the Crusel's machinery. Okay. Yes. Right. And how about matroid version? So we do have an analogous matroid version for matroid pathways. Actually, there was some lower, it's kind of lower bound, but it's not exactly lower bound. So Jisoo-jang and Oh Jang-kwan and myself had a paper saying that the list of pivot minor obstructions should be big. It should contain at least that many distinct graphs. These graphs are pairwise, not locally equivalent. We also have a proof of that. Right? You don't need the 2 graphs pairwise locally equivalent in your list, because then you can remove one from the list and still you have the same effect. So that's kind of lower bound, but it doesn't give you the lower bound of the size, but it says something. And our proof method is based on this paper by Dimitrios and 2 co-authors, and they show that minor obstructions have there are at least k factorial squared many distinct matroid in the list of minor obstructions for paths with k. So in a sense, that's very weak lower bound because there are many. So you take a log of whatever something, then you should have at least the bound should be at least something. But I don't have an explicit lower bound on the size of the obstructions. This is about the counting, right? How many obstructions do you need? Yeah, so these are different type of the bound. And I mentioned already that our theorem can be seen as like constructive algorithm, right? So we can construct the cubic time algorithm to decide whether or not linear rank width is at most k. But we knew it already. This was due to Jisoo and Eun-jung and myself. So we had already an explicit cubic time algorithm to decide whether or not the linear rank width is at most k. And not only that, we are also able to output the optimal layout if the answer is yes. And this doesn't use Crusel's theorem. So we don't use any logic formula or whatever. The algorithm is explicit. If I have enough time, I can implement it. But we will not see output. Extremely slow, right? So yeah, algorithm is based on dynamic programming and runs on the branch decompositions. And what we did for this paper is to use their machinery. So here are the 3 main ingredients of the proof. So the first ingredient is the theorem due to Nagamochi in a conference paper published in 2012. And even though Nagamochi didn't write it explicitly, but I mean, his proof is very short, but he showed that whenever you have a linear layout of width and most k, then you have a linked linear layout of width and most k. So I will say what linked means later. So this is Nagamochi's theorem, I can say. I mean, there might be an earlier paper, but this is the one that I can find. And then there's something called the touch linking theorem. And I had a paper proving the analog of touch linking theorem for pivot minors in 2005. So I used that. And touch linking theorem is analog of Menger's theorem. So like either you have many disjoint paths or you have a cut. And Tut proved the analog of that for matroid, and then we have an analog of that for pure minors. And the last ingredient is the object appearing in the dynamic programming, which is we call the B trajectories. So these are three ingredients. So what is the linkedness? So linear layout is linked if for any pair of cuts. So probably it's better to explain in this picture. So you have a ordering. So I look at, let's say, two cuts. Let's say these two cuts have same width value, same connectivity function value. Let's say 3 and 3. So what does that mean? That means on the left-hand side you have E1, E2. On the right-hand side you have E11 up to En. Now middle ground is arbitrary, right? Now what this says is that the minimum separation separating these two sets, minimum order separation separating these two sets should appear. So the minimum value should appear as one of the cuts here, right? So previously this was cut rank 3, cut rank 3, and I look at all possible separations separating this set to that set, and let's say the minimum value was 2. Then in this sequence I should have somewhere 2. So that's what it means. And why is it called linkedness? There's a concept for path decomposition of graphs. So in the path decomposition of graphs, you have two stacks, and the linkedness is like if you have a minimum separation separating this thing, then there should be some back having this size in the middle. So the path decomposition looks like this. So, maybe I should say the other way around. So if in the path decomposition, it's like if all of them if all the backs have a large size, then you should have these linkages. Okay, if all the backs have size bigger than k, then you should have a k disjoint path. So that's what linkedness means, or path decomposition. But in the matroid, you cannot easily say what k disjoint path means. But you can say that there is no small cut, right? So that's why we talk about the cuts instead of saying many paths. Anyway, the Nagamochi had a paper saying that there is a polynomial time algorithm to find the linear layout of width and most k for fixed k, if there exists a linear layout of width and most k. And the output of his algorithm is always linked. So if you read the algorithm, then it's clear that the output is always linked. So that's why I stated his algorithm like this. If there's a linear layout of width and most k, then there's a linked linear layout. All right, and this is true for any connectivity function or any symmetric or modular functions. So that's the first ingredient. And the second ingredient is the linking theorem. So I had a paper proving analog of linking theorem. So this is again similar. So what is Menger's theorem? So Menger's theorem says that either you have many paths or you have a cut separating them. Now, how do I say there are many paths from x to y in a matroid? Well, you cannot say path, but what you can do is I can contract these edges on the path and delete things outside. then you have a minor. And then you look at the connectivity in the minor, and this connectivity is equal to the number of paths. Think of the graphing matrix. If you have a graph, then I'm going to contract these things and delete all the other edges. Then when you end up is a minor where these vertices will meet both sides. So the connectivity between x and y is precisely the number of edges. So the Church linking theorem shows that either there exists a minor on x union y whose connectivity and this cut is equal to is at least k, or there is a cut whose connectivity is less than k. Okay, so that's the matroid version. And we had the same theorem for pivot minor version. So, and this is one way to write it. So minimum order separation can be realized by certain minor. So there exists a pivot minor so that the cut rank at that pivot minor is equal to the minimum order separation between x and y. And the proof is very soon, very short. It's like 1 page. So why is this useful? The thing is, when you have this linear length decomposition or linear layout, then by the previous theorem, I'm going to assume that we have linked linear layout. Right? So this is going to be linked linear layout of width at most k, no, width at most k plus 1. And then by using this pivot minor theorem, well, by pivot minor, I mean, I have to apply some pivot operation and delete vertices. But why don't we just apply pivoting first and then do the rest? So we may just start by applying pivoting first, and then I can say that, well, even so, just by taking induced subgraph, I already achieved the minimum order separation. So I can just assume that we can delete people in the middle, and I still have a cut rank from here to there. The cut rank is still 3. So that's how we use Church linking theorem. So how do we finish the proof? So let's assume that we have a pivot minor obstruction for graph of linear rank width at most k. Then this graph must have a linear rank width k plus 1 exactly. Now there exists linked linear layout with at most k plus 1. So this height means the width of some cut, right? So you start from 0 and 1, 2, blah, blah, blah. And then I'm going to find, so the height is at most k plus 1. So the numbers are from 0 to k plus 1. So you only have finitely many cases. So if the graph is big, then there will be many repetitions. So I can find many repeated values where all the intermediate values are higher. Okay, so I will find many of these red things where all the other values in the middle are higher than that. This is like pigeonhole kind of thing. And then we can apply Church linking theorem between the first red cut and the last red cut. So I'm going to apply pivoting obtained from Church linking theorem to assume that if I delete anything in the middle, then the connected function value is still preserved. Now I look at the left-hand side of the first cut and left-hand side of last cut. Right? Oh yeah, but actually what I do is find the 2 cuts where they have the same full set. And what do I mean by full set? I didn't explain it, right? Did I skip the slide? No, not yet. So I will try to find the 2 cuts where my algorithm. So remember, I had an algorithm with the Eunjung and Jisoo about deciding whether or not branch linear rank width is at most k. And this algorithm works like this. You just remember all partial solutions and then you move one, and then you update this list of partial solution. You move one, update the list of partial solutions. So no matter whatever you have other information, you have a complete information on the left hand side. So this already determines whether or not your current solution can be extended to a good solution or bad solution. So, and the thing is that this list of partial solutions, there are only finitely many. So that means if this sequence is long enough, then there will be two places where the status will be same. The algorithm will have exactly the same internal variables, right? So, which means that whatever it comes, the output will be same. Okay, so that's the trick. So I will explain more about that. So we will find the two cuts with the same full set, just because there are only constantly many distinct full sets. And then now we prove that, well, even if we ignore in the middle, attaching this, giving this to the algorithm will give me the same answer. So previously, if I give this thing over here, my algorithm would say that, oh, the linear rank list is bigger than k. Now, even if I remove that, the status of the algorithm was still same status with that. So if I give this as an further input, my algorithm will still say linear rank list is bigger than k. That's contradiction, because this was pivot minor minimum. Okay. So that's the sketch of the proof. Now you may wonder what happens with full sets and how did it work. And that's where we use vector spaces, and that's where you could understand why this works for matroid. Right. So given a graph G, I can construct a collection of subspaces like this. So I'm going to construct. So first of all, we define subspace arrangement. It's a collection of subspaces of a vector space. And linear layout of subspace is nothing but the linear ordering of this collection. And then width of linear layout of this collection is nothing but the maximum of this dimension of this thing. So what is this? This is like a span, the span of left intersection with the span of right. This is like connectivity between left and right in the vector space. And I compute the dimension, and that's the width of the linear layout. And then pass with some subspace arrangement, it's minimum possible width of all possible linear layouts. And then from a graph G, so not a graph G. So this is standard basis. So E1 is 1, 0, 0, 0, 0. E2 is 0, 1, 0, 0, etc. Now we have n-dimensional vector space. I'm going to define two-dimensional subspace like that. How do I define? So let's say this is my adjacency matrix of the graph. I should make a symmetric. If this is my adjacency matrix, then you can think of the identity plus this matrix, right? So this is like 4 by 8 matrix. Now, here what I define Vi is going to be span of the first column and the fifth column. So this span of these two is going to be V1. Span of these together with the second and fifth is V2. So that's my construction. All right. Now the collection of them is called the subspace arrangement arising from graphs. Why is it interesting? This is interesting because dimension of, for instance, V1 intersection with the V2 plus V3 plus V4 is equal to twice of the cut rank of the first vertex. Is it clear? So here you have identity part. Here you have a adjacency matrix. Now, what is the dimension of that? I'm taking span of this intersection with the span of the blue, the red part. Span of that, I can, by using this thing, I can make this to be 0. Oh, maybe I'm cheating? Yeah, I can make that to be 0. So, right, I don't need this part because I can clean up. And by the same reason I can clean up this part. So I can assume that this is 0, this is 0. Still, span of the intersection doesn't change. And then it turns out that, so what is the dimension of the intersection? Well, it's going to be rank of this plus rank of that. Because anything they span will be in the intersection with this guy. This is 0, this is 0. Anything they span will be in the intersection with the span of that. So sum of these two rank of 2 matrices, but they are symmetric. And cut rank function was this, rank of that. So it's twice the cut rank function. Okay? So that's why we can convert the graph problem to a vector space problem. So path width of this subspace arrangement is nothing but twice the linear rank width of graph G. But if you plug in the one-dimensional subspace, then instead of graphs, you have the matroid path width. So for graphs, it's 2-dimensional subspaces. And then this is a definition of the trajectories. So what is it? So this is about how we're gonna encode our solutions, and like we have partial solutions: E1, E2, E3, E4, E5. Yeah. How do we create things? Well, I cut somewhere, and then I look at the span of left-hand side with respect to some small vector space B, and span of the right-hand side with respect to this B. So that's R. So this is L, this is R. So L is going to be span of these things with respect to B. R is span of those things with respect to B. And lambda is, I compute the span of that, dimension of span of that with the span of that. But there will be some number. That number could be bigger than L intersection R, dimension of that. So that extra dimension you need is going to be a lambda. I didn't say here, but so what kind of thing? So this is like an easy property then, right? Because when you move on, the left-hand side is getting bigger and bigger. That's why L is increasing, and right-hand side is getting smaller and smaller. That's why R is decreasing. And yeah, so this is the, for the subspace arrangement, this is like definition of the left, definition of right, and definition of lambda. So intersection of the dimension minus the intersection in the L and R. So this is like a data structure that we store, but still there are too many. So this is what's called the canonical B trajectory of a particular linear layout. And there are too many. It depends on the size of input. So how do we compress the amount of information? What we do is we do apply some operation called compactification. So we can remove an entry if it's repeated. And also, when you have a sequence, if all of them have the same left space, same right space, but the sequence in the middle, the numbers in the middle are just sandwiched by the first one and the last one, then we can remove all the middle ones. This doesn't change the outcome of the algorithm. So that's the thing. So you can repeatedly apply these operations and then get an optimal one, get something that you can no longer apply any of these operations, then we call it compact. And so we say that UKB be the set of all compact B trajectories of width and most K. And the key thing is that when you have a vector space of bounded dimension over the finite field, then the number of compact B trajectory is bounded by constant. It's some constant dimension, the constant number. And then this is the information that we are trying to store during the dynamic programming. This is a set of all compact B trajectories of width and most K, such that there exists another B trajectory realizable. So which means it's a canonical B trajectory of some optimal solution, realizable in B, which is less than or equal to gamma. So this comparison relation I didn't define, but it's like subspaces are the same, but numbers are less. So for each, so L, so I can, yeah, I mean, maybe it's better to skip the definition of the comparison. And then we had a theorem back in 2017 that a full set is non-empty. Full set is non-empty if and only if path width is at most K. And also you can deduce all these lemmas from the previous papers. So basically what it says is if you have two left configurations with the same full set, then whatever you combine with the right hand side, the output will be same. Right? So this one, so you have two, let's say you have one left hand side, one another right hand side. I attach with this and attach with that. And this is the first matroid, the first subspace arrangement, the second subspace arrangement. If the full set from 1 is same as full set from 2, then when you combine them, you're gonna have a same outcome. So if this has linear rank, the path width at most K, then this will have path width at most K. So that's it. Okay, so here's a list of open problems. The first one is, can you find the bound for matrix pathways independent of size of field? It'd be nice to have something for arbitrary matroid. So for branch width, the proof works for matroid, regardless of representations. So 62K works for branch width, any matroid. But for path width, we don't know. And we also want to have a better lower bound. Okay? All right. That's it. Thank you.
Any questions?
Yeah.
Is there a chance that you can get rid of the dependence on the field if the field has dimension 1? I just don't, in the formula you listed, it seems that if theta equals 1, then maybe.
Oh, you mean if theta is 1? Yeah. Well,
I don't know.
Yeah, but the thing is, so this B comes from the, so theta will be eventually K plus 1. The thing is, this B is coming from, so we already know that it has a linear path width at most K plus 1. So we're gonna use dynamic programming on this path decomposition of this K plus 1. So this B is the space coming from the decomposition of this K plus 1. So theta is gonna be theta is gonna be K plus 1. Yeah. Right. But I think if theta becomes 0, the problem will be easier. Yeah.
Any other questions?
So your group also hold for the representable data?
Yes. So when you have a representable delta matroid, you can just construct the corresponding the subspace arrangement, and the proof will go through. I think. Yeah, probably.
Can you give a hint why your result with Geelen implies the Kuratowski's theorem?
Oh,
Is that, like, super hard?
You mean this obstructions for pivot minors? Yeah, the thing is, so circle graphs. So bipartite graph is a circle graph if and only if it is a fundamental graph of a cycle matroid of a planar graph. That's from paper in 1981 by French mathematicians. So that's why we could imply such a thing. So if you have a planar graph, for instance, so fundamental graph is like you pick a base and take the like look at the base versus non-base elements and put an edge. So if I pick a base, yes, I have colors. Yes, I have the colors. If I pick a base, so what is going to be fundamental graph? 1, 2, 3, 4. So 1, 2, 3, 4, and this edge 5, 6. 5 is adjacent to 1, 2, and 6 is adjacent to 3, 2, 3, 5, 2, 3, 4, right? So how do I construct this? So whether or not this is bipartite? No, this is bipartite, but whether or not this is circle graph? Around the spanning tree edges, you can draw a circle, and then rotate the edges inside the spanning tree by 90 degrees, and then flip those edges inside. Then you get a chord diagram where this is 1, this is 5, this is 2 and 4, 3 and 4, and this one corresponds to that, and that corresponds to, I think this, yeah. So this graph is the intersection of the intersection graph of the chord. And so so our theorem characterized circle graph in terms of pivot minors, but if you have a bipartite graph, then all pivot minors are bipartite, because pivot operation never destroy bipartiteness. So if I apply this theorem to bipartite graph, then bipartite graph is circle graph if and only if it has no pivot minor in these. But some of them are non-bipartite. So if you eliminate non-bipartite one, then only 3 graphs remain. And so this one, that one, and there should be one more. This one? Oh yeah, no.
Next to the grid.
Oh, this one? No. This one, yeah, right. Yeah, so these 2 plus that, those 3. So one of them is the fundamental graph of matroid. One of them is a fundamental graph of K5. One of them is fundamental graph of K33. So that's why we can deduce matroid never appear as a fundamental graph of graphic matroid, and so you only remain two things, K5 and K33. Does that make sense? So that's how we deduce it.
Any other questions? Okay, then thank you again for filling in.
Thank you.